You clicked because you want to understand the real limits of artificial intelligence, not the hype. The problem is that the models working perfectly in simulation are failing catastrophically when they touch the physical world. By the end of this, you will understand why automating scientific discovery requires more than just raw computational power, and how the very tools we build might be narrowing the scope of human knowledge. There is a profound tension between the rapid technical capability of modern artificial intelligence and the hard constraints of physical reality. We often treat AI as a pure software problem, assuming that if the algorithm is clever enough, it will solve anything. But in the real world, latency, power consumption, and sensor noise create a wall that no amount of training data can simply erase. A model might predict protein folding with stunning accuracy in a digital environment, yet fail to account for the thermal fluctuations in a laboratory reactor or the electrical noise in a sensor array. This gap between simulation perfection and industrial reality is where the true engineering challenge lies. Consider the distinction between what researchers call easy problems and hard problems. Easy problems involve optimization within defined constraints. We are seeing breakthroughs here, with AI successfully navigating complex optimization tasks in protein folding and fusion reactor design. These are domains where the rules are known, the variables are bounded, and the goal is clearly defined. The machine excels because it can iterate through millions of possibilities faster than any human. But there is a consensus forming that AI currently cannot address the hard problem of formulating novel scientific questions. Automating science requires conceptual revision, not just computational power. This brings us to a critical paradox emerging in the scientific community. AI tools are significantly boosting individual productivity and citation impact. A researcher using these tools can analyze data, generate hypotheses, and draft papers at a rate previously unimaginable. Yet, simultaneously, these tools are contracting the collective scope of scientific inquiry. Instead of exploring new frontiers, AI tends to automate established, data-rich fields. The result is a narrowing of topic diversity. As more researchers lean on these tools, they gravitate toward the same well-trodden paths where the data is abundant and the models perform best. This reduces overall researcher engagement with truly novel, high-risk areas of study. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. The definition of artificial intelligence is evolving from a static technical concept to a dynamic science of human behavior. We are moving from passive tools for analysis to agentic systems capable of autonomous execution. This shift has the potential to trigger the next intelligence explosion, but it also highlights a critical knowledge gap. We still do not know how to engineer agents capable of automatically inferring and updating scientific paradigms. This capability is currently reserved for human cognition. We can build machines that optimize, but we have not yet built machines that can fundamentally change the framework in which they operate. To bridge these gaps, researchers are proposing new directions. We need neuro-symbolic systems that combine the pattern recognition of neural networks with the logical reasoning of symbolic systems. We need agentic frameworks that allow for flexible operations rather than rigid execution of predefined scripts. We also need to utilize large language models as instruments to study human behavior rather than merely optimizing them for safety or productivity. The goal is to ensure that AI expands rather than restricts the boundaries of human knowledge. Here is the thing that often gets missed in the excitement. The democratization of artificial intelligence literacy is happening at an unprecedented pace. Structured, short-term curricula now enable beginners to master foundational concepts in weeks rather than years. This rapid adoption is double-edged. On one hand, it empowers more people to contribute to the field. On the other hand, it accelerates the contraction of scientific focus. When everyone is trained on the same tools and the same datasets, the diversity of approaches shrinks. The system becomes highly efficient at solving known problems, but increasingly fragile when faced with the unknown. The boundary of the hard problems in science is being redefined. Challenges that were previously intractable are now being solved, while some traditional research areas become obsolete. But this obsolescence is not always a clean replacement. It often means that the unique human intuition required to spot a new direction is lost in the noise of optimization. We are optimizing for what we can measure, rather than exploring what we cannot yet quantify. This creates a feedback loop where the system reinforces its own biases, making it harder to break out of the established paradigms. The future progress of this field depends on shifting our focus from pure optimization to understanding the cognitive processes that drive human innovation. We must stop asking how to make machines think faster and start asking how to make them think differently. The next leap in intelligence will not come from scaling up current architectures. It will come from designing systems that can engage in the kind of conceptual revision that humans do when they encounter a paradox. This requires a deep understanding of how humans form hypotheses, how they discard old models, and how they navigate uncertainty. We are standing at a threshold. We have the tools to solve the easy problems, but we are still searching for the key to the hard ones. The tension between the speed of automation and the slowness of human insight is the defining challenge of our time. If we do not address this, we risk creating a future where science is highly efficient but stagnant, where we solve every problem we know how to ask, but miss the questions that could change everything. The path forward requires intellectual honesty about what our current paradigms can and cannot do. We must engineer systems that respect the physical constraints of the world while pushing the boundaries of what is conceptually possible. This means building agents that can infer new paradigms and update their own operating assumptions. It means valuing the messy, non-linear nature of human creativity over the clean, linear nature of algorithmic optimization. Only then can we ensure that artificial intelligence serves as a catalyst for discovery rather than a cage for our collective imagination. The next intelligence explosion will not be defined by speed alone. It will be defined by the depth of the questions we are able to ask. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.